All right. This is chapters 15 and 14 and 15. Guys, you have seen this. Oops, I hate it when I do stuff like that. You've seen this before. It was also on the acid-base retest, but remember now we're not learning new stuff. We're just learning how to activate the pathways. So, reactivating the pathways. You should already know this. So you're going to see me flip back on these first two questions because you remember that there's three kinds of acids basically. Binary acids that don't have oxygen in them, so their real name is going to be like hydrogen bromide, hydrogen chloride, hydrogen fluoride, hydrogen iodide, hydrogen sulfide, and then there's ick, I ate it. So I'm going to flip back and forth so that you can see like where I'm getting the names. And so on this first one, by the way, what makes something an acid is that the positive ion is hydrogen. So the first thing you'll notice is that these all have the same positive ion. And then if you look over here, the ClO minus one ion is called hypochlorite. Notice that hypochlorite has oxygen in it, so this is an oxy acid. So this guy's real name is hydrogen hypochlorite. And because of that, it's an oxy acid. And all you need to remember for oxy acids is if the negative polyatomic ion ends with ite, when we convert it over to the acid name, we just switch ite to us, acid. And then if the polyatomic ion's name ends in ate, we switch over to ic acid, just the suffix. And so switching colors, so hypochlorite turns into hypo. Look at, keeping everything the same. Just keep in mind that the only two that are different are sulfur and phosphorus. Hypochlor, and then we drop the ite and we put us acid. Fabulous. Okay, next one. H is hydrogen. And then we're going to go find that SO3 is called sulfite. You will see that. SO3 is called sulfite. Make sure you just find it without any hydrogen, because we also have the hydrogen sulfite ion. And so, oops, this is crazy. That's supposed to be over here. So anyways, make sure you take all the hydrogens off and just use sulfite. And you come over here and number, I said sulfur and phosphorus. They're a little different, although this is an oxy acid, so we're using these rules. I said take off the ite, but this is not sulfus acid, it's sulfurous. Oops, switching colors. Go over this. Sulfurous acid, because sulfur and phosphorus, you have to put in this extra syllable so it flows off your tongue. So this is sulfurous acid, not sulfus acid. So sulfurous acid. This is the other one. Notice here I am again doing sulfur and phosphorus. So this guy's real name is hydrogen phosphate. Again, it's an oxy acid. It's an oxy acid, so I shake off the 8, and it's not phosphoric acid. Sulfur and phosphorus are the weird ones where you have to put in the extra syllable. Don't worry about this on a multiple choice final. Phosphoric acid will be there. Phosphoric acid won't be there. So just, you're fine. You'll be fine on the final. For the first time, guys, this is a binary acid, not an oxy acid. They are named very differently because they're the only ones that have a prefix. So this is hydrogen iodide, not hydrogen iodate. If you go over here, if it doesn't have oxygen in it, it comes from up here. I minus 1 is iodide. And because bi means two, and there's only two things here, when you name these, they start with hydro, and that's because there's only two things in them, hydrogen and something else. So this is hydro from the hydrogen. The stem is iode, and then these also end with ic acid. because binary acids are the same as the 8 ones, except to tell them apart, they put a hydro in front. So if this was HIO3, it would be iodic acid, but because it's not, it's a binary acid, it's hydro. Sorry, there's an O in here. Hydroiodic acid. And then this is an oxyacid again, so the real name is hydrogen oxalate. And if you don't recognize that that's oxalate on the final exam, don't worry. If it's not on the sheet, it won't be on there. But if you look, the C2O4 polyatomic ion is called oxalate. And so then when we do this is, remember, if it's an oxyacid, so I got to remember 8, you just cross off the 8 and put ic, or you cross off the ite and put us. And if it's a binary acid, you have to worry about this extra prefix hydro, but this isn't. And so I just take off the 8, substitute ic, and then this is called oxalic acid. Again, this will be easy. It's multiple choice. And so you just have to recognize. Okay, I think it's a little bit tougher proposition to go the other way because, okay, first of all, this one starts with hydro. This is the one that's going to be the binary acid. Hydro, not hypo. So all of the rest of these are oxyacids. So all you have to remember is ic, I ate it. So here we go. This one's real name would be hydrogen acetate because the stem is ACET, and then I switch the ic and I go back to 8. And then you go to your ion sheet, and hydrogen is +1, and acetate is C2H3O2 -1, +1 -1, slam them together. This is going to be HC2H3O2. Let me go back and show you on the ion sheet that acetate, they're in alphabetical order, C2H3O2 -1. It's right there. Oops-a-daisy. So this guy, this is the tough one because this must be hydrogen, and then it's not sulfate, it's not sulfite, it has to be sulfide, because if it starts with hydro, it doesn't have oxygen. And on the ion sheet, hydrogen is +1 and sulfide is -2. And +2 and -1 don't add to 0, so I have to haul out the crisscross rule. So this is H2S. This guy's real name has to be hydrogen bromate, because ic, I ate it. So bromate. Bromate is one of the new polyatomic ions that we put on the sheet for Chem 3 so we could get all the acids. So bromate is BrO3 -1. And so then hydrogen is +1 and bromate is BrO3 -1. And you can just slam those together. Keep forgetting to switch colors. HBrO3. Hypochlorous doesn't start with hydro, so this is hydrogen hypochlor, and I take off the us and I switch ite. And by the way, guys, you're seeing this hypochlorite because almost everyone in the world uses bleach, which is sodium hypochlorite, which comes from sodium hypochlorite is a salt that you get when you mix this acid with a strong base. Anyways, comes up a lot in real life. Hydrogen is +1, and if you go over here at the bottom, it's a new ion that only comes up in acid-base chemistry. Hypochlorite is ClO -1. And so this is Cl for chlorine, O -1, +1 -1. Just put them together, and so this is HClO. And then finally, chromic acid's real name is hydrogen. I don't even care. I'm not switching colors. Chromate. Doesn't end with hydro, so it's an oxyacid. Ic, I ate it. On the ion sheet, hydrogen is +1, and chromate is CrO4 -2. And +1 and -2 don't add to 0, so the 2 comes here and the 1 goes here, and this is H2CrO4. Okay, and next slide. This is really important stuff. So what you need to do is this is a Bronsted-Lowry reaction because there's two things on the left, two things on the right. You have to find two pairs. Here's the blue pair. Here's the green pair. Okay. These are called conjugate acid-base pairs. There's two of them. One of them, they can only differ by one more or one less proton. So they have a difference of one proton, either one proton up or one proton down. Green pair, this guy had one hydrogen, or sorry, I'm doing the blue pair. This guy has 0 hydrogens or protons. 0 or 1 goes to 0. The hydrogen went down. Acids give away their hydrogens, they're proton donors, which means this is the acid, and then this guy is the conjugate base. And then green pair, this guy had 2, now he has 3. Bronsted-Lowry said that bases are proton receivers, and so if it goes up, it's called a proton acceptor or receiver. And Bronsted-Lowry said that proton donors are acids, and proton receivers are bases. And so in the green pair, this is the base, this is the conjugate acid. Next slide, blue pair has to be here. Oh, I guess that's green. Can't even tell my colors. Here's the blue pair. I do the blue because I still got blue. 1 hydrogen, no hydrogen. This is the acid, which makes this the conjugate base. And then this has 1, 2, 3, 4, 5, and this has 1, 2, 3, 4, 5, 6. Bases go up, so and this is the conjugate acid. Okay, just a little bit of practice. These are the worst problems. You guys are awful at these. So here's the deal. We got H2SO4, which is a diprotic acid, and it is reacting with NaOH. And I can do words, but we've done this a lot. So what you end up with is, water, because anytime an acid reacts with a base, the H comes off the acid, because acids are proton donors. The OH comes off the acid, the H comes off the acid, the OH comes off the base. HOH is water. And then the salt is going to be sodium sulfate. But if you notice on your ion sheet, sodium is +1 and sulfate is -2. So you're going to have something like this. And the reason why this has to be a 2 is if you have 2 protons, you have to have 2 OHs to neutralize them. And so this is the balanced equation. And then it says we have 49 mils of, okay, what is the molarity of a H2SO4 solution if 49 mils? So basically we have 49 milliliters, and they want to know the molarity. And then we know the concentration here is 0.333, and this is 68.4 milliliters. And then remember, now we never do stuff in milliliters. It has to be in liters. So 1, 2, 3, this is 0.0490, and then liters, and then this is 0.0684 liters. And then remember, this means moles per liter. And so titration always works the same way. Here's my U flow. So this is step 1, and this is step 2, and then step 3 is going to be this 1 to 2 mole ratio. And then what makes, and then this is step 4. I remember that in titration problems, you always multiply moles per liter times liters first, because that gets you into moles, which is the most important concept in all of chemistry. And then you use the mole ratio, and then the last number gets flipped. So very quickly, 0.0684 liters of NaOH. And you could put this over 1 if you want a top and a bottom. And then 0.333 moles of NaOH per 1 liter of NaOH. And the beauty of titration is mole per liter times liter. It's always moles. And then for every 2 moles of NaOH, because of the single monobasic, this is 1 mole of H2SO4. And then remember, the last number always gets flipped. We want the molarity of the H2SO4. We have the moles in the proper position. It's up. We have to get the liters in the proper position, which is down. So this is 0.0490 liters H2SO4. And so now this won't cancel, which is good. We want to be in moles per liter. And so then if you put this in your calculator, it's very interesting. What comes out of your calculator is 0.282 moles per liter, or molar. This one, you have KOH, which is potassium hydroxide, and it's being added to hydroiodic acid. And what happens is, this is monobasic, this is monoprotic. We're just going to put these together, HOH. And then the salt is Ki, and this is a 1-to-1 mole ratio. And then, so now we have 76 mils of a 0.742 molar hydroiodic solution. I always put the volume down first, but it doesn't matter because multiplication is commutative. It's just the way I do it. And then they're telling you that this is 1.22 moles per liter, and they want to know the volume. Probably milliliters, but it's going to come out in liters. And then, so what happens is, and remember, you always have to be in liters. So this is 0.0760 liters. Here's your U flow. This is step 1. This is step 2, moles per liter times liters. Those will be moles. Step 3 is the 1-to-1 mole ratio. And then this is step 4, but keep in mind, step 4 is always inverted. And so let's come down here and try to write a little bit smaller. 0.0760 liters of HI, that's hydroiodic acid. And then this is 0.742 moles of HI per 1 liter of HI. And then for every 1 mole of HI, you need 1 mole of KOH. And now this is the interesting part. If moles of KOH is in the bottom, this 1.22 moles of KOH has to go down or it won't cancel. And that's 1 liter. And so what you got to realize is this answer is going to come out in liters, not milliliters. And then we're going to have to multiply by 1,000. And so when I did this, what the calculator says is 0.0462 liters of KOH. But we're going to go 1, 2, 3, because all chemistry glassware is calibrated in milliliters. So 46.2 milliliters of KOH. Okay, this is, you got to have a chart. These are the tough ones. So remember, this is what Arrhenius says. HCl makes H plus. And then if this is +1, this has to be -1. You can do it by looking here. If H is +1, then chloride has to be -1, or you could just reason it out. And then you have to set up a BE chart. This is an easy BE chart. You got to put M here, or you got to write it down every single time. Although it's multiple choice, I won't know. This is 0.0038. This is 0, this is 0. Let's talk about this. In the very beginning of a chemical reaction, with all reactants, no products. At the very end, there's no products, all reactants. And so what happens here is, at the end of the BE chart, we know that the hydrogen ion concentration in solution is 0.0038 molar, because that's what this means. Okay, by the way, what the BE chart tells you is if it's an acid, at the end of the BE chart, you should know the H plus concentration. If it's a base at the end of the chart, you should know the OH minus concentration. Now, I want the pH. So you got to remember that H plus is related to pH, and OH minus is related to POH. And what relates these two concepts is that pH and POH have to add to exactly 14. And so the question is, we know H plus, and so it's very easy to get the pH because we're solving for something that starts with a P. It's the negative log of 0.0038. When you put that into your calculator, you will get 2.42. Now this problem is a little tougher in a lot of ways. Oh, I know what I want to say on this last one. Because it's a 1-to-1-to-1 mole ratio, all of these are the same. But what you're going to notice on this problem, and you guys are really struggling, some of you, with writing this. Arrhenius said that bases make OH minus. But how many OH minuses? 2. If this charge is -2, this charge has to be +2. You can reason it out, or you can get it off here. Ba is +2, OH minus is -1, and that's why the formula for barium hydroxide, because if barium is +2 and hydroxide is -1, the crisscross rule guarantees that there'll be a 2 down here. And so basically what we're doing is doing this backwards. Okay, then we do our BE chart, because in the beginning, 2.7 times 10, you have all reactant, no product. At the end, you have no reactant, all product. This is 2.7 times 10 to the negative 5, and this is 2 times 2.7 times 10 to the negative 5, which is 5.4 times 10 to the negative 5. You could do this 1, 2, 3, 4, 2, 7, right? 1, 2, 3, 4, 5. Plus 0.00027, 14, carry the 1, 5, and then 0, 0, 0, 1, 2, 3, 4. However you want to do it. This is what we know at the end of the BE chart. We know that the OH minus concentration, because this is like an Excel spreadsheet, what is the ending concentration of the OH minus if it's a base? Or what is the ending concentration of the H plus if it's an acid? This chart tells us that this is 5.4 times 10 to the negative 5th molar. Now, its pH is related to POH. These got to match. It starts with the P. It's the negative log of 5.4 times 10 to the negative 5. Because of this, I know it's going to be between 4 and 5. This has 2 sig figs, so I need to have 2 decimal places. And if you do this on the calculator, you will get that the POH is 4.27. But I didn't ask for the pH. I asked for the didn't ask for the POH. I asked for the pH. So 14 exact minus 14.27 is 9.73. All right, and then I think when I was setting this up the other night, instead of doing the chart, here's what we know. We know that H plus is 2.5 times 10 to the negative 7 molar. Remember, brackets mean concentration. pH, because H is related to pH, is the negative log of 2.5 times 10 to the negative 7. This has 2 sig figs, so this has to have 2 decimal places, and this is 6.60. And then POH is 14 minus 6.60, which is 7.40. And remember, we're keeping 2 sig figs on concentration and 2 decimal places on pH and POH, because this 6 is coming from this, it's got to be between 6 and 7. That's how logarithms work. And so the sig figs are only after the decimal point. Now, what's OH minus? Well, that doesn't start with the P, so it's going to be 10 caret negative 7.40. And that is 4.0 times 10 to the negative 8 molar. Cool. Just a calculator drill. On this one, what do we know? We know OH minus. So now OH minus is 0.0039 molar, or if you prefer, 3.9 times 10 to the negative 3. The reason why I kind of like this way is because I see, oh, negative 3. It's going to be between negative 3 and negative 2, but the POH is the opposite log. Now, the OH minus is related to POH. So, and it starts with a P, so this is the negative log of 0.0039, which is 2.41, between 2 and 3, just like I said. pH is 14 exact minus 2.41, which is 11.59. And then H plus, now this doesn't start with the pH, so I use the exponential base 10. So if it starts with the P, you use the log key. If it doesn't start with the P, you use the 10 key, because they're inverses. And so 10 to the negative 11.59 is 2.6, 2 sig figs, times 10 to the negative 12 molar. All right, so now this is interesting. If the pH is 8.53, then H plus, now this doesn't have a P in it, is 10 to the negative 8.53, which is, looks like it's 3.0 times 10 to the negative 9. And then because it's a concentration, we got to slap the M on it. All right, now pH and POH are related by the 14 thing. So this is 14 exact minus 8.53, which is 5.47. And then finally, OH minus is, it doesn't start with a P, so it's 10 to the negative 5.47. And this is 3.4 times 10 to the negative 6 molar. Fabulous. And then same thing, POH is 2.72. I'm going to do the OH minus first because pH is related to OH minus. This is 10 to the negative 2.72, which last time I checked was, my calculator said 0.0019 molar. If you prefer, 1.9 times 10 to the negative 3. And then the pH is 14 exact minus 2.72, which is 11.28. And then H plus, because these two are related and these two are related, and what relates the two halves is that those have to add up to 14. This is 10 caret negative 11.28, which is 5.2 times 10 to the negative 12 molar. Oops, I forgot to do acidic basic, so let's go back. If the pH, always focus on the pH. The pH is less than 7, it's an acid. 6.60 is less than 7, so this is acidic. And then pH here is 11.59, that's greater than 7, so this is basic or alkaline. And then this basic is better. Find pH 8.53 is greater than 7, so this is basic or alkaline. And then finally, find the pH 11.28 is greater than 7. This is basic or alkaline. Okay, chapter 17, crazy thing. I could not figure out how to get this chart in there, so I thought when I was doing this, I would quick write it. So what we have is we have trial, 1, 2, 3, and then the first reactant is A, and then this concentration is 0.34 molar, 1.02 molar, and 0.34 molar. And then the other reactant is B, and this is 1.8 molar, 1.8 molar, and then 3.6 molar. And then we measure the rate of formation. Anytime it says formation, it means it's a product. rate of formation of Ba3, and this is in moles per liter per second, which I would call molarity per second. This is 0.090, and then this is 0.27, and then this is 0.36. This is actually cool because I can use colors. So to find how A2 affects the rate, I find a set of trials in which B is held constant and A2 isn't. That's right here. So purple. 1.02 divided by 0.34 is 3. So in trial 1 and 2, the concentration of A2 goes up by a factor of 3. The concentration of B does not change. And this concentration goes up by 4 because 0.27 divided by 0.090 is 4. Sorry, I lied. This is 3. 9 goes into 27 3 times. So 3 to what power gives you 3? 1. So it says first order. Now, to find what B is doing to this, you find a set of trials in which B changes, but A doesn't, and that's 1 and 3. So here, there's no change. Here it doubles because 3.6 divided by 1.8 is 2. And here it quadruples. That's the one I was thinking about because, holy mackerel, that's crazy. I have no idea what I did there. So this is going to be 0.36 divided by 0.09. This is the one that's 4. So 2 to what power gives you 4 is second. And so what we know is, and this is all you have to do on the final, so you don't have to calculate K. What is the rate law? Well, the rate law expression, they didn't ask for the rate law. It is some K, which we're not going to solve for, times the concentration of A2 to the first power times the concentration of B squared. And that's all I asked you to do. Just do the rate law expression because that's actually all I ask you to do on the test. Okay, overall reaction. So here we go. This C cancels with this C, and this B cancels with this B, and this D cancels with this D, and this F cancels with this F. And so the overall reaction is A plus 2E goes to G. What are the intermediates? Okay, so let me just do this. A, B, C, D, E, F, G. From doing this, I know that G is a product, and A and E are reactants. So B, C, D, and F are intermediates or catalysts. Let's look for catalysts first. Is B there in the beginning? Yep. Is B a reactant? Nope. Is B kicked out at the end? Yep. B is the catalyst. And then C isn't there in the beginning. It comes in the middle and it goes away in the middle. D isn't a catalyst. And that's it. C and D and F. C, D, and F are all intermediates. And then, so what are the intermediates? C, D, F. What is the catalyst? B. By the way, it didn't ask you to do molecularity, but let's go back and just say they did. Just because. So then if you do that, step 1 is bi, because 1 plus 1. This is ter, because 1 plus 2 is 3, and this is bi. All right. And then chapter 18, write the equilibrium expression for the following reaction. So the first thing you got to do is remember it's right over left, and you got to have K, and then it's NO, and it has to be in brackets, and then because of this 4, we need a 4 here, and then this plus changes to times, and then it's H2O, and because of this 6, you need a 6 here, and then over NH3, and because of this 4, you need a 4 here, times O2 to the 5th. By the way, those are all gases. Let me grab this eraser. There's no solids in here. So nothing gets crossed off. Again, here, nothing gets crossed off. This one, K, is going to be the concentration of NO2, because it's right over left, squared over the concentration of NO squared times O2 to the first. And then it's, so it's 2 to 1 to 2, so you should have two 2's and a 1 as exponents. This is 4 to 5 to 4 to 6, so the exponent should be 4, 5, and 4, 6. And then K is the concentration of CH2O. This is a 1, so we don't have to write down the 1, but you can write down the 1 if you want. It's kind of implied. And then this is CH3OH. You can write down the 1 if you want. All right, so then this one's crazy. The first thing I'm going to do is write down the equilibrium expression. So we got K is equal to NH3 squared, because of this 2, over N2. This plus changes to a times, and then this is an H2 cubed. And then it says an equilibrium mixture is determined to consist of 0.602 molar N2. So where N2 goes, actually I should go down. It's good form to go down. N2 is 0.602, and that does not have to be squared or cubed. And then 0.420 is H2, but that has to be cubed. And then this is 0.113. NH3, which is in the top, is 0.113, but that has to be squared. And you just have to be able to put that in your calculator. And you would type it in like this, 0.113 squared divided by, and then parenthesis, 0.602 times 0.420 cubed. And if you do that and you round to 3 sig figs, you are supposed to get 0.286, so 0.286. Okay, and then here's just one example, same thing, except now we're going to solve for something else. So K is concentration. It's right over left where the stoichiometry becomes the powers. And so, and then this one's interesting. Switch colors. So they gave you the equilibrium constant. So K is 1.3 times 10 to the negative 2. N2 and H2 are both found to be 0.1. So this is 0.1. And then this is also 0.1, but that has to be cubed. And then what is the concentration of this? This is what we're looking for. So we're calling that X, but that has to be squared. So then when you take cross products, switching to purple, this is a very easy cross to do. 1 times X squared is 1X squared. This cross is 1.3 times 10 to the negative 2 times 0.10 times 0.10 cubed. And if you put that in, that cross ends up being 1.3 times 10 to the negative 6, which kind of makes sense because this is 1 times 10 to the negative 1, and this is 1 times 10 to the negative 1, so negative 3, negative 4, 5, 6. What undoes the square? A square root, and now X is 0.0011 because you get 2 sig figs molar. Finally, last thing, Le Chatelier's principle. Okay, what happens? Le Chatelier says, so you have a system at equilibrium and it's stable, like a teeter-totter, and you do something to make this side go down. If you want it to get back to where it was, you either have to push on this side or push up from the bottom. But in other words, in order to get back to where it was, you have to do the opposite. So if you increase this guy, nitrogen monoxide, it doesn't like that you increased it. It switches to the side that gets rid of it. So this would cause the equilibrium to shift to the right. If you decrease O2, it doesn't like that you decreased O2. It tries to replace it by switching to the side of the equation that replaces the O2. This would cause the equilibrium to shift to the left. If you increase NO2, it doesn't like that you increased it. It tries to decrease it by switching to the side that doesn't make it. So this is shifts to the left again because it tries to get rid of it. The volume ones are the very most difficult, and I think you guys struggle because you got to get a sense of what decreasing volume is. When you decrease the volume, you made it smaller. Okay, and there's more crowding. And it wants to undo the stress of being more crowded by switching to the side that's less crowded. This side has 3 moles of gas. This side has 2. And remember, it always does the opposite. When you increase, it tries to decrease. When you decrease, it shifts to increase. If you make it more crowded, it switches to the side that's less crowded, which is the right. If you increase the temperature, that actually just means you made it hotter. It doesn't like that you made it hotter. It tries to relieve the stress of being hotter by switching to the side that's colder. The right side produces heat, so this side must absorb heat. So that would cause it to shift to the left. And then these are the craziest of all because you have to remember your gas laws. Sorry. If you decrease the pressure, you increase the volume. That's when I put the marshmallows in the vacuum pump and we sucked out the air and the marshmallows swelled. This means you made it less crowded because increasing the volume means you made it bigger. And so it's less crowded. And so it doesn't like being less crowded. To get back to where it was the most stable, it wants to reduce that stress of less crowding by switching to the side that's more crowded, which is the left. And I think that is it. Good luck on your final. I'm going to push stop.